So in this video, we're going to talk a little bit about springs and elastic energy. Now, hopefully you've already done the spring activity that was on your class website, and you saw a little bit how that type of thing works, which will give you a little background in this. But we're going to talk a little bit more about springs and that type of stuff. Now, when people think about springs and elastic energy, two things that often come to mind are, of course, springs and, of course, things like elastics, which are two really common things used to store elastic energy. Now, elastic energy is actually a really awesome type of energy for lots of things. It can use for so many different functions, whether it's springs in the type of spring that might be like in a pen, or the springs in the shocks for a vehicle, or how many things use a spring to move it back and forth, like buttons and a whole bunch of stuff, or even elastics where you can stretch them and stuff like that. And these are the two things that most people really think of a lot when thinking about elastic energy. And like stretching a spring or compressing, these are two ways that you can store energy. And a lot of people, when they think about stretching, they think about rubber bands, and stretching or compressing a spring, either way, doesn't make any difference. These are two really common ways that we can store elastic energy. Another really common way to store elastic energy is to actually bend stuff, like here we got like a pole vaulter. So you can actually bend stuff as well in order to store elastic energy, whether there's a pole like this, or maybe it's like a hockey stick, or which flexes when you use it. Anything where you're going to bend something and it can actually then snap back or move back, it's storing a form of elastic energy. So bending stuff is another great example. There's also stuff like this, and there's a little catapult, and kind of harder for you to see, but right there you can actually twist things as well. So it's got like some elastics or ropes or strings in there which are twisted, and that can also store energy. So often we will twist things and then they'll sort of twist back and release that energy. Another really much more common one recently over the years is something like this. Here we have an air compressor, and it's using like compressed air is another great way to store energy. I mean, this is how like a lot of Nerf guns work and stuff like that, where you have air, you have like CO2 cartridges, you have tools that are air powered. It's all about using compressed air. So stretching and compressing springs, bending things, twisting things, compressing things like air, these are all different ways that we can use and store elastic energy. And you can see like it's used for lots of different things in lots of different ways. Every single day you're using it. It's whether even just walking in your shoes, when you push down the shoes, they push back, like there's so many different things that actually uses elastic energy. So when we talk about elastic energy, it's a great form of energy. Okay, so it's a really common way to store elastic energy. Well, it's a little better. So it's a really common way to actually store energy using all of those things that I've got listed up here. And there's more than this, but these are just some of the really common ones. And one of the great things about it is you can actually store it, and then you can actually save it for later. So you could like stretch a spring or elastic or compress something, like especially like these two things over here, and then you can like just wait for later. You don't have to use it right away. Something like this, obviously, bending the pole, obviously is using that right away. But you could twist something, compress air, you can stretch, and you can actually save it for later and use it for whenever you want. Okay, it's also very portable. You can, have an air compressor. You can compress the air. You can throw it in a vehicle, drive it somewhere else, and use it somewhere else. So it's super portable. You can save it for later. There's lots of different things you can actually do with it. So it's really handy. Also, like pretty much any size, like really large applications for it, really small ones. There's tiny little springs and tiny little elastics. There's even like a lot of buttons and keyboards have little tiny pieces of metal or plastic that bend when the keys get pushed up and down. And it's lots of different applications. So it works really well for lots of different things. Okay. Now, when you guys did your little lab type thing, and you did an online simulation, you saw how elastic energy works, that type of stuff. One of the basic fundamentals things that you guys did is there was a graph and there was a force distance graph. And often for springs and elastics and that type of stuff, instead of using D for distance, you typically use an X value. Sort of distinguishes it a little bit in terms of being a distance for a spring or elastic, because it's not actually necessarily going anywhere. Like looking at a D sort of implies that it's actually traveling a distance from one place to another. So it's often really common to use the X for that type of thing. Anyway, so when you guys did your lab, your online lab, you do force times distance, you will get pretty straight line is what you should have got, something like that. And this is just the basic relationship for basic springs and elastics. Basically, the farther you want to stretch or compress it, the more force you have to use. And if you've ever stretched an elastic or a spring, you know the easiest time to actually move it or stretch or compress it is at the very, very beginning. Because as you stretch it further, and further, or compress it further and further and further, not only do you have to apply force to move it farther, but you also have to apply force to hold it in place. So first of all, you stretch out an elastic, you have to hold it, using force just to hold it in its stretched position, and then you got to use more force to stretch it even farther. So the further it goes, the more force is actually required. So you get a nice linear relationship, and of course the slope for this is your K value, which is the spring constant, and that was in that online activity lab that you guys did. So this slope is your spring constant, and this is connected to Hooke's law for springs and elastic devices. Now this is just a basic, very, very simple linear type graph. So it's basically y equals mx plus b. The b is 0, goes to the origin. And so if we sort of do the formula for it, force would be equal to kx, and that's it. So that's how you can calculate how much force is required to extend or compress a spring or elastic, just F equals kx. So it's actually pretty simple. It's not that big of a deal. Now, the other thing that we can look at in terms of this is we can actually apply other things as well. We can try and find out the energy that is actually in the spring. Now, you guys have done energy and work and that type of stuff already, and the work to compress the spring or extend an elastic, whatever you want, the work done would be force times distance, and this is of course stored as potential energy. So this is the potential energy that is stored inside the actual spring. So if we sort of piece this together a little bit, the work to compress or stretch a spring would be FD. Now you've got to be a little bit careful because this right here is the average or constant force. And when you're using a spring or elastic, the force is not constant. The force is going to change as you extend or compress it farther. So gotta be a little bit careful with that. But what we can do is we can actually work with this a little bit. If we want to find the average force, that would just be the maximum force used just cut in half. So this would just be that maximum force that was used just cut in half divided by 2, and we would multiply that by the distance, and that would give us the force that was actually, the work that was actually done to move the elastic device. So if we sort of work with this then, this is also the same force. This is the force up here. We can actually take this right here and we can actually put that into here. Now the other thing is that distance that we're talking about, that is also the x value. That is how far we are stretching and compressing the spring. And if we sort of put these two things together, we've got that divided by 2. I'm just going to pull that out as 1/2. And then I've got, instead of writing the force, I'm going to use the kx. So that is going to be my kx. And then instead of d, I'm going to write x again. And then you get 1/2 kx squared. Okay, so this can be used to calculate how much work or energy is stored inside of an elastic device if it's stretched or compressed, like a spring or elastic or something like that. So relatively straightforward expression, very similar to the kinetic energy one with the 1/2 and the squared over here. And as you can see, that x value is really important. as you stretch compress it further and further, it requires way more energy and way more work to actually make it function the way it is. Now, another way we can actually look at this is similar to what you guys have done before. If you go to FD graph, you guys have done this before, that the work is actually the area under the graph. So if we would calculate the area of this, that's another way to find the work in an FD type situation. So if I did that, it's just the area of a triangle, 1/2 base times height, right? Well, the base is your x value. That's your x value. The height is the maximum force that was used, and we can piece it together this way. And you can sort of see this will end up being the exact same thing that we had over here. So this is going to just be, we got the 1/2, we got maximum force, and we've got the x value again. And then you could do the exact same substitution for maximum force as being kx, and you'll end up with the exact same expression that we had over here. So basically there's two ways to calculate how much energy inside of a spring. You can do F equals kx to find the force, then work equals Fd. It's got to be careful that this force right here has to be the average force. You got to cut in half. Most people just jump to the 1/2 kx squared if they can, and then calculate the energy that way. And then what you can do is you can take that energy and then apply to things. This can be turned to kinetic energy. Maybe it does some other kind of work. Maybe it goes to gravitational potential energy. There's lots of different things that energy can go to. So it's just another type of energy, and then that can be connected to other types of energy conversions.